Hello, in this video we are going to see how we can simulate a microstrip transmission line in CST. So in our previous video we have seen that what are the main characteristics of the microstrip line. So here we are going to see how we can design that in CST and how we can find the line impedance, electric field distribution, magnetic field distribution and S parameters. So this is the question where we have to design a microstrip transmission line having characteristic impedance of 50 ohm on FR4 substrate having thickness 1.6 mm. So this D is 1.6 mm and W we have to find out epsilon R is 4.3. So let's see that. So for that, calculating the equation, we can use this equation. So this is a piecewise equation. Here you can see that the equation is divided into two, where W by D is less than 2 and W by D is greater than 2. So in our previous video, we have seen that we will be going with the first equation, and after calculating W by D, we will be checking if this condition is met, or if not met, then we will be calculating again with the second equation. So for first of all, we will be considering W by D is less than 2. Now we don't know the value of W by D, but we are going with the assumption that W by D is less than 2 and we are going to use this equation. So for that equation, we need the parameter A. So to calculate A, we are going to use this equation which depends upon the characteristic impedance and epsilon R. Epsilon R is 4.3 for FR4 and is a 0 is our requirement 50 ohm. So substitute all these values here and find out A and substitute that value of A in this equation and find out W by D. So W by D we get it as 1.93. As this 1.93 is less than 2, we can assume that our assumption is correct and we can go ahead with the calculation. So W can be calculated by substituting D in this and it will be equal to 3.09. If otherwise, we can also use some online calculators. So this is one of the online calculator from Pasternak. Here you can substitute the values and calculate the impedance. So here it is the other way around. So we have to substitute some bit values and have to find out the impedance. So this is one of the method that we can use. Otherwise, in CST also there is an inbuilt calculation tool where we can calculate the width. So let's go to CST and start simulation. Let's do that. So let's start with CST. Go for microwave RF optical antennas template. You can go for planar and time domain. Frequency I'm going to select from maybe 1 to 10 and finish. So in CST also, if you want to calculate the width of the uh, microstrip, you can use this option, calculate analytical line impedance. It will show this calculator. So it has different options like calculating for coaxial cable strip lines, microstrip lines, etc. So you can select the microstrip option and you can choose the thickness what is desirable to you and the width. So it is like calculating the other way around. So means you have to optimize this W value so that you will be getting what is the value required in characteristic impedance. So previously, as we have calculated the value as 3.09, I just put that it here, and here you can see that the characteristic impedance is around 50.45. So that's one of the way that how we can calculate the microstrip width. So let's start. First of all, we can start with dielectric, and I'm going to use different length for the width and length. So the thickness is H. So we are going to use FR4 substrate. So preview, then DW I'm going to use it as around 30 and DL in maybe DL maybe 35. Okay, H is 1.6. So we have the dielectric, and next is the ground plane. So it is also the same dimension as the dielectric. So it is on the ground plane and the material is PEC. So the ground plane is also created. Next is the trace. So for that we have calculated the feed width. So you can use that value in FW as it is on the top of the patch. I'm going to use H plus 0.035. I'm going to assign some thickness for the feed. So feed we have calculated as around 3.09. So we have the feed now. So our next aim is to assign the ports. So you can zoom in and you can select the face. For that you can use the option pick face. So F is the shortcut for selecting the face. So if I click F, I can select the face, and for assigning the port it is always better to use the macros. You can go for solver ports, calculate port extension coefficient. Here you can see that the width is already selected based on the selected phase. Then you can just click construct port from picked phase, so it will be automatically creating the port. Here you can see that the port is contained within the dielectric. Next is we have to assign the port on other face. So click on F, select it, and repeat the same method. Solver ports, calculate port extension coefficient, and then construct port from picked face. Okay, so it is, so we have two ports. So now our aim is to just see the electric field, magnetic field. So here we can see that the bottom is already electric. So to reduce the calculation domain, one thing you can do is you can select the EZ min as electric, as it is already PC on the ground plane, and maybe you can use, because this port is assigned along the y-axis, then we have to assign the air boundary along the y-axis only. Here you can just use the boundary open because we don't have any port along that direction. So this boundary you can use so that it will be reducing the calculation domain. And next is we can assign some field monitors. So maybe we can use the, okay, 5.5 is okay. So electric field, we are going to use the electric field and the magnetic field. So now we have the field monitors, and you can go to the time domain solver and you can start the simulation. If you want to improve the accuracy, you can increase this value and you can select the adaptive mesh refinement. I'm not going to use that because my system is not that much powerful, and you can start the simulation. Okay, the simulation is complete. Let's check the results. So one of the main parameter is the S parameter. So we have to check S11. So S11 here you can see that it is very below minus 10 dB. That means that whatever the signal is coming here, it is getting transmitters. That means there is no reflection. So S21 also gives an indication about how much power is getting transmitted. So here you can see that it's very near to the zero. That means that all of the signal is getting transmitted. So the both S11 and S21 gives an indication about the performance of this feed. Here you can see that there is no reflection, and all of it is getting transmitted. Similar performance we can obtain for the port 2 also. Here you can see that if you consider S11 and S22, both have the same performance, and S21 and S12 has also the same performance. And now we have designed this feed for a 50 ohm impedance, right? So it was showing around 50.4 when we are using the calculator. So to check that value whether it is coming correct or not, what you can do is you can go to the port information and this line impedance. So this line impedance gives an indication about the impedance. So here you can see that the impedance offered by this feed width is around 48.5. So it is near to 50 ohm. This is the impedance offered by this line. So that is the characteristic impedance. So we may have to optimize this feed width little bit to get the correct line impedance of 50 ohm. So this is how we are making sure that the feed width is actually matched to the uh, designed impedance. Okay. Then another parameter that is of interest is electric and magnetic field. So that can be seen here. So if you click on the port 1, you can see the electric field, how the electric field is distributed here. So maybe I will hide the port. So if you click on this port and select both these things and just press Ctrl H, it will hide. Otherwise, you can just right click and hide this port. I'm going to hide the bounding box also so we can have a better view. So here you can see that how the electric field distribution is happening. So here you can see that how the fringing is happening across. So we have seen in our presentation that how the electric field distribution is happening. So here you can see that the electric field are coming from dielectric to ground plane. So you can note this arrow. So all this arrow are coming from this patch to the ground. So the similar thing can also be seen here. Here also you can see that these lines are coming from patch to the ground plane, and through the fringing also every field is coming from the patch to the ground plane. And next is the magnetic field. So here, so if I drag, it will be increasing, sorry, it will be decreasing the range and you will be having a better vision. So just drag it so you can have a better view. So here we are seeing the magnetic field. So here you can see that the magnetic field is literally forming a closed loop around the patch. So you can see the direction of arrow here. So this is what we have seen here. So here you can see that the magnetic field is actually following these circles. That is what we are seeing here. Okay. So this is the magnetic field which is showing circles around the patch. So you can use this electric field orientation also just to see this. So for that you can use the field on cut planes and you can select different cut planes, maybe 0, and make sure that how it is happening. So here you can see that how the electric field is oriented. So if you select this one, you can see the field performance on the port 2. And okay, so H field means we have seen from this port also how the H field is oriented. So you can either use this port information or this electric field and magnetic field information to see how these fields are varying in the microstrip line. So because of this fringing field, that is, as the you can see here that the field is not only constrained within this dielectric, it is also going through the air. Because of this, this is not actually a TEM, this is a quasi TEM. That's why this we are saying that the microstrip transition line is supporting quasi TEM because of this fringing effect. And then maybe you can So now one of the main disadvantage of using this transmission line is it will be having spurious radiation. That means that some of the energy will be leaked from this end of this feed line. So that is one of the disadvantage of this microstrip line. That is why we are going for the CPW, because the spurious radiation is very less in case of CPW. So that can also be seen from this field monitor plots. Okay, maybe I will use the contours. So here you can see that how these fields are getting extended. So that is, it is not actually confined within this trace. It is getting means extended outside the trace. You can see it is getting extended. So if it is placed inside in a PCB and there are some components coming near to this trace, these extended field will be affecting that. So this um, electromagnetic interference will be more if we are using these type of microstrip transmission lines. So this is one of the disadvantage of microstrip transmission line, these spurious radiations. So if there are any other trace nearby, there is a chance of getting it affected. So this is what it is. And okay, I hope we have discussed everything. So we have seen the electric field, magnetic field, and how these spurious radiations are happening. Any other things? I hope everything is okay. Then I hope you get some idea about this microstrip transmission line and how you can simulate it and how you can identify what is the actual line impedance that we are getting, and if it requires any modifications, or how the electric field and magnetic field orientations are happening. Thank you.